Hello everyone, and welcome to this lecture of Reliability Partners and Unblocked Systems. Your host today is Nwebedu, and I preferably go by the name Grace. I currently work as an SRE and have spent several years focusing on reliability engineering in distributed systems. I've spent the last 3 years building our permission systems, network like Hyperledger Fabric, because check out my GitHub, it has the link, and yeah, I work styles, I like philosophy and mathematics. So in this talk, we're going to explore reviewing architectural and personal patterns that can help keep your fabric network highly available and resilient to failures. I'll walk you through everything on how to cluster needs and force tolerance to handling Byzantine scenarios to practical performance tuning. And yeah, maybe in the end, we'll talk about reward ethics. Yeah, these are session overview. So pretty, we're going to have a fabric overview so that we're aligned on the basic components of like the fabric network. Then next, I will dive into fault tolerance node clusters, focusing on peers and ordering. Then we'll look at Byzantine fault tolerance and how fabric is evolving in that area. Then after that, we'll discuss network partitioning, how you handle network partitions. Things like this happen, bad things happen. Then next, we'll talk about performance tuning, high availability. Then we'll cover monitoring, alerting strategies. So you can detect issues early. Then we'll review real-world failure scenarios. From there. What is Fabric? Hyperledger Fabric is a modular permissioned blockchain framework or system. So unlike public blockchains like Bitcoin or Ethereum or Solana, it's designed for environments where participants are known or semi-trusted. So you are going to find this in governments, or you are going to find this in financial institutions or supply chain, that kind of Fabric main components. Peers, the host ledgers and smart contracts, which you could also call chain codes. Then the ordering service puts transactions and put transactions into blocks. So we'll see how Rust and DST can be used there for reliability. Then membership service or CS, certificate authorities, they issue and manage identities. Then chain code is the smart contract logic. Chain codes are stored of peers. So what chain codes do is to endorse and invalidate transactions. We're going to talk about how to prevent that time data loss and have catastrophic failures in such a system like this. And Fabric, the way Fabric is designed for reliability, it does like a distributed system where each and every kinds of do replication. It contains the console of variables that you can either run Raft, PFT, events, Kafka also deprecated. And yeah, the way this spheres sync is, or the way this system sync is through the code protocol. Yeah, this is an example diagram of multi-organization fabric network. In this organization, in this network, there are about 4 organizations. The root organization, which the ordering service would run. An established pattern is to have a separate, or there are only, but yeah, this network has about 3 organizations. Organization 1, 2, and 3. And if you look at each of these organizations have at least one pair running in them. A good example of a network that's built for redundancy will have at least 2 pairs on them. So if you could organization 1 is running about 8 pairs, and organization 2 and 3 are running 1 pair each, and also like the ordering service, the root organization is running about 3 others which are built on Raft. So as this store goes on, I think a lot of things will make sense here. Yeah, if you notice, each of these organizations are running ACA to manage identity. The big picture here is that each org has multiple peers. These peers talk to the ordering nodes to get blocks. So the way each of these components talk is through the gossip protocol. So we rely on the gossip protocol for peers to share ledger data among themselves. Yeah, like I said, and architectural patterns, each of 2 to 3 pairs for redundancy, protocol for just saying the audience service could have 3 to 5 others. You just an odd number because possible runs on this thing. And yeah, if you're running Raft, yeah, we'll get more on that. Yeah, CA, the cluster running with that CA might not be a problem. CA is if your CA goes down, that will probably be a problem. The network will still run, but this clients have to reuse certificates, or you want to error new certificate, it becomes a problem. So you probably want to have a backup on it. And yeah, if you're running Kubernetes, the feature of Kubernetes is called anti-affinity. You want to spread the peers or others pods across different nodes. You don't want one of them running in same Kubernetes node, because if that Kubernetes node should go down, for example, you have your whole network going down. In this section, we're going to talk about fault tolerance node clusters, how you build for node level fault tolerance. So, like I said, in Fabric, you have 2 types of nodes, the peers and the order service. The peers, at least each org should have at least 2 or 3 peers. Oftentimes, an input network tray. If one fails, the other ones can endorse transactions or self queries. Gossip ensures that they keep it as consistent ledger copy. Yeah. For the ordering service, you typically run 3 to 5 others if you are using Raft for crash fault tolerance. If one fails, the cluster will select a new leader as long as they see a majority of. So Raft is based on leader-based consensus. So at every time the cluster leads the leader, there's an leader election that goes on if a leader crashes or dies. And if you want higher fault tolerance, it could go as high as 5 nodes. So in 5, we'll probably be able to tolerate 2 crashes. So keep adding for higher fault tolerance. You should ensure it's a high number. So you also want to make sure you are not adding a lot of things, because you want to make sure that you are not having so many nodes that throws out the cluster from equilibrium. This architecture is crucial, because if we had only one node, or if we have only a single pair, any downtime will just force the network, the entire network. You could see why this is important. The way Raft works is by having a node. So we'll just talk a little bit on Raft mechanics. Raft works by having one node as a leader. That leader proposes transaction batches. When in majority, the node or followers acknowledge, the block is considered committed. If the leader fails, one of the followers steps up and becomes a leader. So in a 3-node cluster, losing one node doesn't necessarily stop the show, because you still have 2 nodes forming a majority. That's how we keep ordering online despite hardware failures or crashes. Yeah. So to avoid single points of failure, to summarize, the key is to avoid single point of failure. No single orderer, always a cluster. Multiple peers for organization, you want to have 3 at least. So if your identity issuance is mission critical or very important, you want to have a backup C. And if you are running on Kubernetes, you want to set up anti-affinity to make sure that pods are not essentially on this. As a rule of thumb, you consider your failure domains like region, data center, or even the rack, and spread the nodes accordingly. So let's talk a little bit Byzantine fault tolerance. So Fabric default consensus is crash fault tolerance, which means that's Raft. Raft is crash fault tolerance. But what if your nodes could be outright malicious? For example, one of your nodes is trying to reorder the order of transactions. So yeah, that is a form that doesn't take care of. Byzantine fault tolerance means that can tolerate nodes that actively misbehave or attempts to fork the chain or attempts to crazy things like reorder transactions. So Fabric introduced a BFT ordering service for BST in preferred country. So this requires 3 nodes to tolerate failures. Means if you want, for example, if you want to tolerate 140 node, you need to have 4. So that is 3 times 1 plus 1. Yeah. So area F is the number of failures or malicious nodes you want to be able to tolerate. So if you want to be able to tolerate 240 or malicious nodes, that's 3 times 2 plus 1, which is about 7 units. So it's more resource intensive and has more of a method overhead. You get a stronger guarantee, but you get a stronger guarantee that the network will be consistent, even if some participants act manually. The use cases for this is if you are in an environment where you don't really trust the other members. VFT is really suitable for this, or in very high value finance environments. To summarize, Raft handles crash failures well, but not malicious ones. So BFT can handle both. Most deployments would not immediately jump to BFT because it's still something very new in Fabric. But if you have a use case for truly untrusted participants, then it's worth evaluating. So let's look at handling network partitions. So real distributed systems must handle like a case where the network itself fails or it becomes segmented. So let's discuss federal partition. Let's say the set of orderers partition themselves. So with Raft, the partition that has a majority of orderers would continue producing blocks. So the minority side stalls doesn't create a fall. Once the partition fails, the minority automatically catches up. For pair isolation, if the pairs are isolated, they stop receiving blocks. When connectivity returns, they do gossip-based cancel, pulling missed blocks from the healthy pairs. So as architects, we want to distribute nodes across different zones or data centers so that we can still achieve a majority even if a region is cut off. This is a partition diagram. This diagram shows that the majority partition keeps ordering going while the minority stores. So the big takeaway here is that no forking happens, right? So the minority side eventually sinks once the network is restored. So let's discuss performance tuning, high availability. Reliability is not really just about redundancy, it's also about ensuring that system can handle load without failing. Just like some tips. Increase block size for throughput is also meant to watch for latency. You have to tune this for your workload. If possible, use more looser or flexible policies, e.g. any 2 of 3 orgs can keep you running if one of the org is down. So strict policies can cause a stall or halt if a required authorization goes offline. Then also, like for the state database, LevelDB is faster, but CouchDB supports regex queries. That adds like some form of overhead. Then you also want to have multiple channels like parallelizing workload for scalability or isolating issues. Fast SSD, enough CPU, you want to ensure that you have beefed out the hardware level, so enough CPU, memory, SSD, and even network bandwidth. Rolling upgrade, update one node at a time. So to avoid total update. So this is a sample Raft config. So you can see in the excerpt how we define conceptors in orderer.yaml. So this is sample orderer.yaml for a Raft cluster. The key parameters here like tick interval, election tick, and heartbeat, it can be tuned based on the network latest. Many times, default values are often fine, but in high latency or global deployments, you want to increase them. So yeah, you can see this election tick, heartbeat tick, and also constants. So this is an endorsement policy example. It's like a JSON snippet that requires any 2 or 3 ops. So this means that one op could be completely offline, but will still be able to get valid endorsement. This is much more resilient than a policy that is requiring all 3, which means that if one organization stalled, then the whole network is stopped, or transaction in the whole network is stopped. Yeah, for monitoring and alerting, so you want to proactively catch issues. So we need monitoring. Key signals include like node health and container restarts. You want to also look like block production rate, ledger high to detect lag in those. You want to also check transaction throughput, latency, resource usage, and expiry. So a popular combo is a Prometheus plus Grafana, but if you can use stuff like ELKs, you can also use stuff like ELKs Plug for log analysis. Or things you want to alert for, no new blocks has been created, or even resource extraction. Yeah. So yeah, that's like proactive alerting you could do is detect anomaly early. So you want to check if the raft leader has changed. You want to check we want to alert on caustic failure or monitor stuff like this. And if possible, you have taken metrics or logs for a long time. You want to do like historical trend analysis on this. These are some, even with all these factors, some things can go wrong. So let's look at some examples. Ordering node crash. Raft would quickly elect a new leader and the event will continue. So this needs no really manual intervention here. So peers out of sync, gossip sometimes can automatically catch up. Only feeling probably the next network failures outside of fabric. Org down, strict endorsement policy probably has frozen the network, or we don't have enough organizations. Set expiration. I think a famous case of this is what happened with Sticker on PBDC when it went down for more. When I worked at Gala, the chain was also based on Hyperledger Fabric. There are some instances where set expiration was big issue. Yeah, but sometimes too, things like a chain could bug, like a container can panic, but other peers and also there's partial continuity. Network partition, only majority side continues, so minority will be stored until it reconnects. Sometimes you have like denial of service attack. They are validating with proposals that leads to new endorsements or maybe even a store. This is going to lead rate limits. So from this incident, we have seen like even setups, flexible policies, automatic renewal SaaS, and thorough monitoring are crucial. So in all of these, I think monitoring is really important. So there are some industry use cases and industry use cases of Fabric. We have seen Fabric in financial services, in Fabric in supply chain. In financial services, is typically like multi-region deployment, 3 to 5 drafting. If they like, they could also use BFD. Also, zero downtime updates and very heavy on monitoring. Supply chain, this is high volume, so you need parallel channels, and you also have to wait. Data is always available, even if some peers fail. For identity systems, very security focused networks, they'll possibly adopt BFT for malicious false tolerance. In every of these cases, the ops team heavily invest in monitoring, scaling, and testing. Best practices, like a recap of best practices, You want to have redundant pairs and ordering nodes like redundant components. You want to have flexible endorsements for a single org endorsement before, and you also don't have to require every org. Regular certificate management and backup of admin credentials, some block sizes and endorsements for your workload, active monitoring, actively monitor, also failover and rolling upgrades to minimize downtime. And yeah, to test your assumptions, you could shut down or simulate in partition to see if the network recovers. Like, so that's the chaos testing. So the conclusion here is Hyperledger Fabric can be very reliable if we take advantage of its architecture, if we distribute other replicate pairs, set up thoughtful endorsement policies, and build a solid monitoring program. We have looked at both Crawford tolerance and Byzantine port tolerance, and how to handle network partitions, and how to fill performance, and how to avoid real-world pitfalls like certificate expiry. So by following these reliability patterns, you'll be well on your way to a resilient enterprise-ready fabric network. Thank you for your attention. And yeah, I hope this was a good talk and gives you some perspective on how to design reliability patterns in permission blockchain systems. Thank you.